So what I want to show you is how, I guess kind of a reverse of this, where I'm showing you a way to wrongly apply this to how a particular situation, when you look at it just slightly differently, you could get at the correct special formula or wrong, rederive it wrong. Okay. So yeah, I think all of this will be a lot less abstract once I have a particular problems I'm giving you, which your homework will be posted soon, which hasn't been posted yet. So let me just try redoing length contraction with the Lorentz transformation. So call that length contraction with Lorentz transformation. And I figured out what I did, quote unquote, wrong last time. I was having the ruler move because that's the setup I had. But for the particular kind of mistake I want you to make, I actually had to have the ruler stay stationary. So let me say the ruler is staying stationary. What is actually moving is not the ruler, but you. So let me draw the picture this way. This would be the space-time diagram. Sorry, this is position. This is time. So given this space-time diagram, so ruler is in the stationary left frame. So let's say that the ruler has length LP, and this is the ruler of length, the proper length LP. And just to finish it, the word line or the trajectory of ruler would look like this. This is the trajectory of the end of the ruler that's at the origin, and this is the trajectory of the end of the ruler that's not at the origin. Good. Now, so let's say we want to rederive length contraction using this space-time diagram, illustration, and the Lorentz transformation. So we do the same thing as what we were doing last time, except wrongly this time. So you have the coordinate. You have the coordinate of one end of the ruler. This is 0, 0. By the way, I'm going to ignore the y and z coordinates since nothing interesting happens there. And the coordinate of this point here would be, so time is still 0, so along this line here. And x coordinate is now the proper length. Okay? So this is what someone might do in trying to rederive this length contraction. Let's say, all right, so I know Lorentz transformation. Ct prime is equal to gamma Ct minus beta x. X prime is equal to gamma x minus beta Ct. I look at the, so I guess this is going to state the origin, so let me not worry about this. I'm just going to see how this point transforms. So once again, the ruler is staying stationary. You have to imagine that you are in the frame that's zooming by at speed v. And as you are moving, you are measuring the length of the ruler. Do you expect the ruler to contract, as we said in length contraction? Yes. So imagine, I want you to think about this before we get to the answer, because if you don't, it can get confusing. So let's say this is the ruler you are holding, and this is the ruler that's being held here. So if they were at rest, they would be the same length. Sorry. All right, same length, 12 inches. And when you are making measurement, this is what's happening. So this ruler stays with the room. It's at rest. You are zooming by at, I don't know, half the speed of light. And as you are zooming by, you compare these two rulers. And this is the question I'm asking. Which ruler would you find to be shorter? Would you find this ruler to be shorter or this ruler to be shorter? A or B? How many say A? Okay, how many say B? Okay, so Kian, why would you think B might be shorter?
Your reference frame is the one that's moving?
Yeah, so you are staying, so you are the one, so, okay, let me just let this ruler stay here. This is in the left frame, it's not moving. You are the one moving. So I'm moving like this, and as I'm moving across, I see, okay, measure it against each other, and then keep moving. So I, as an observer, or you as an observer, this ruler is the stationary ruler to you. Yeah. So is this the moving ruler from your perspective? As you're moving by, yeah? Yeah. So according to the special situation where we derive the length contraction, you would expect this ruler to be shorter to you as you are measuring it as you're moving by. Okay? So that's the expectation. So we are looking at the coordinates here, and so we are given the coordinates in the left frame. Now you want to express it as the coordinates in your reference frame to see how you would measure it. Good? Okay, let's finish writing this out. So let me plug in these numbers. So CT prime, that's going to be 0, plug in 0 for t and LP for x is equal to gamma 0 minus beta LP. Plug in the same numbers here. So LP for x, gamma LP minus beta c, 0, sorry. So it's 0 again, minus 0. And this is what you're measuring. X prime is the coordinate where you measure. And this is what you're finding. X prime is equal to gamma LP. Is that what you're expecting? No, gamma is bigger than 1, right? So if the coordinate of this is greater than, or gamma times LP, then it's greater than LP. So that's not quite right. What happened? So when I take the coordinate of these 2 points and transform it into my reference frame, why didn't this coordinate give me the correct length of the ruler in my reference frame? It's the time. So this is a quite puzzling thing, and we will go over 2 more paradoxes. That's going to appear quite puzzling until you come to realization with the fact that simultaneity is relative. So I picked these 2 points in the ruler's rest frame because they were a simultaneous point in space-time. So imagine me measuring length of the ruler. So this is a quite common implicit convention that everyone uses without explicitly saying it out loud. If I'm going to claim that this, whatever I have is the length of the ruler, I better be measuring the 2 positions simultaneously at the same time. Now, when it's at rest, I guess it doesn't really matter if I measure this end and then wait a long time and then measure this end. Right? Then okay, then it doesn't matter. But it starts to matter. The ruler doesn't quite move easily. Let me use this cart. If this cart is moving and I'm claiming to measure the length of the cart, then it matters that I'm taking the positions at the same time of the 2 ends. If I'm doing this, if I'm getting position of the front and then some later time get the position of the back, you wouldn't think that I'm measuring length of the cart, right? So whenever we are measuring length of something, we insist on simultaneous measurement. And the moment I say simultaneous, you should be wary because you have been told multiple times that simultaneity is relative. And actually, it's represented in the expressions we've written down so far. Here, when you actually finish calculating the t prime coordinate, it's not 0 like this was. t prime coordinate will actually turn out to be minus gamma beta LP. It's at an earlier time. And you guys saw me draw this coordinate axis for the primed coordinate last time. Let me draw it again. So this is the primed coordinate, t prime. And this is the primed coordinate, x prime. Everyone okay with what this axis represents? Like if we had to describe the set of points that make up the x prime axis, what would you call it?
Like the zero position, your position?
It's not zero position, right? This position is at some value that's not zero.
It's 0 time for the t prime reference.
It's 0 in time. Yeah. So these are the set of points, all points where t prime is equal to 0. Good? So you could call this the line of simultaneity. Every point along this line is simultaneous in your moving frame. So, so any other line of simultaneity would be parallel to this. So, let me draw a line of simultaneity that goes through this point. That would look like this. So these are all points where t prime is, I guess, apparently that. So minus gamma beta over c LP. Good? Yeah?
What causes them to be at less than a right angle, the x prime and t?
These are just the set of points that you would plot. If you take the Lorentz transformation and simply plug it in, all right, I know my x-axis represented t equals 0. So I want x prime axis to represent t prime equals 0. So plug in t prime equals 0. See what the equation that describes it. Yeah. But we'll get to more of this when we talk about the geometry of space-time. There's a deeper reason behind it that I don't want to get hung up by right now. But at the moment, if you understand that these are the correct axes for x prime and t prime, then that's all I want to have so far. Good. So for t prime, just to complete, so these are all points where x prime is equal to 0. And this is more intuitively easier than this, but it's the sort of symmetric side. All right, so going back, this line of simultaneity, so this point in your moving reference frame happens at an earlier time. So let's see, how would I put this? So let's just imagine this cart, well, okay. This is my ruler, and I guess, so in this reference frame, it's not supposed to be moving. So we are trying to describe it in the reference frame that's moving to the right relative to it, right? So from your own moving reference frame, what it actually looks like now is it looks like the ruler is moving to the left, right? That's what it would look like from your reference frame. And let me tell you what these two positions represent. As this ruler moves to the left from your perspective, what we have done in marking these 2 points down is this. I have measured this position, let me make it move slower. I have measured this position, waited a while, and then measured this position. In any sense of the word, did I measure the length of the ruler? No. Because if I'm going to claim that I measured the length of the ruler, I should have done it simultaneously in the reference frame where I was measuring. So this is where you have to be careful with the length contraction. When I use these 2 points, I didn't measure correctly. I had to, so in the moving reference frame, the point I should have used to correctly measure the length of the ruler is this point. The point that's simultaneous with the origin. And the graphical representation of the ruler being simultaneously measured in your reference frame would look something like this. So let's say you are not satisfied with measuring the end point. You want to, I don't know, take a picture or measure the position of every single point on the ruler. Then these are the points that represent the measurements you are making. In your reference frame, these are the points of simultaneity. But in this ruler's reference frame, it's not. Somehow, as you're passing by, if you took a picture with a camera, the ruler would see those points of light as striking it in a sequence. Like it strikes one end, strikes, I guess, so the ruler would see it as this end being struck first, and then so on for the rest of them. Because from ruler's reference frame, this point happens earlier compared to this point later. Right? So let me do the correct derivation of the Lorentz transformation for the third time. Last Thursday by mistake. So what I really should do is I should try to get this point here and get the x prime coordinate of that point. So I guess I first need the, let's see. So I know it's x coordinate. So its x coordinate is still LP because the ruler isn't moving in its own frame. And I have to get a new time, t. I think there I can be helped by knowing what this line represents. This line, it comes from here, having set t prime equal to 0. So it's the line that satisfies ct minus beta x is 0. Or solving it for time, it represents t equal to beta x divided by c. Good? Yes? So this is a point on that line. So I plug in this as the value of x, LP. So the time should be beta LP over c. Good? All right, so let's transform these points using Lorentz transformation and see if we get the result that we were supposed to get the first time around. So the time coordinate is gamma times, this is the time, c beta LP over c minus beta times x, beta LP. And this works out to be 0. I mean, that's like by design. I want you to pick a time coordinate that was going to be time that's simultaneous with the origin. Good? All right, let's finish this here. So I need to have the correct value of t really for here. I don't really care about the time coordinate as long as it's simultaneous. It really matters here. So gamma times x, so LP minus beta c times the time, beta LP over c. By the way, if you see me keep writing down this c, this is where you would eventually begin to understand why theorists often work in the units where c is equal to 1. So that they're going to cancel out in the end. You don't want to keep writing it down. But, for this class, I will, so that I don't unnecessarily confuse you. So simplifying this a little bit, I can factor out LP to the right. So it's gamma times 1 minus beta squared times LP. What is this again? 1 minus beta squared? 1 over gamma squared, right? Take this, square it, take the reciprocal, that's this. So this is gamma divided by gamma squared, LP. So you get the result that you are hoping to get, that the x prime coordinate you measure is LP divided by gamma, or the length contraction.